Today, I'm very excited to introduce an alumnus of the program rather. Nic Dobbins is the Principal Solutions Architect at UW Medicine Research IT at the University of Washington in Seattle. He received his bachelor's from the University of Minnesota and master's degree in library and information science from the UW iSchool. Nic's PhD in biomedical informatics from the University of Washington explored the intersections of cohort discovery, dynamic database query generation, question answering, data discovery, human-computer interaction, and natural language processing. Nic is the creator of Leaf, an open-source cohort discovery application used at academic medical centers and commercial companies around the world. And his current research focuses on cohort discovery and autonomous agents driven by large language models, or LLMs. Today, he'll be giving a talk titled Enabling Research with NLP-driven Cohort Discovery and Query Generation. Again, I'm really excited to have Dr. Dobbins here, and I will now hand it over to him. Thank you so much.
So thank you again, and Happy New Year, everyone. It's really great to be here. It's an honor. My name is Nic, as Bhargav said, and I'll be talking today, again, about enabling research by NLP-driven cohort discovery and query generation. I've done variations of this talk fairly recently, so if there's any overlap and you kind of heard some of it recently, I apologize, but I'll try to keep it interesting. Here are my disclosures. Really quick about myself, just to give some context before I get started. And I'll kind of go through this quickly because Bhargav kind of covered a lot of it, but I finished my bachelor's at the University of Minnesota in 2008. I lived abroad in Japan for a few years and kind of focused on perfecting my Japanese abilities. And then I came back to the United States in 2011 to attend the iSchool. And it was there that a really important event happened. And I was able to work with Dr. David Dale in the International Neutropenia Lab and Registry. And that's really where I kind of got set down this path in my career trajectory I've been on, and I'm really thankful for that. In 2013, I did some work called the Neutropenia Clinical Dashboard, and that won the capstone of the year in the iSchool. And since then, I've worked at UW Medicine, first in the data warehousing space, next in what became the Research IT Data Services team. That evolved into a software development position. And for the past several years, I've worked as the Principal Solutions Architect in Research IT here at UW Medicine. I created the prototype of an application called Leaf, which I'll be talking more about in 2015. I began my PhD journey in 2018 and completed that in summer last year. And I completed the prototype of the LeafAI application, which I'll also be talking about in 2022. So I'd like to frame today's discussion and talk really around, much of it of, focusing on my kind of PhD journey and dissertation work and the specific skills and kind of domain areas that are really interesting to me within that. So I'll start by talking about cohort discovery, and we'll define that. Then look at natural language processing, or NLP. And then the intersection of those two, looking at how NLP can enable and in some ways simplify and make more intuitive the process of cohort discovery. Then focus on user interface design. How do we make applications for that useful and intuitive to researchers? And finally, end on some work I'm really excited about, autonomous agents, ambient HRs, and other directions. So cohort discovery is the process of finding patients meeting certain criteria relevant to a potential study. So if we imagine an electronic health record with millions of patients here on the right, and say we're interested in those over age 65, hypoglycemic, and maybe they're left-handed. And imagine we find 1,400 or so patients. So we have discovered a cohort. Now, this is often used in things like prep to research, for hypothesis generation, power calculations, in clinical trials recruitment, and so on. And it can be done in various ways. This could be by manual chart review, reviewing electronic case report forms, or queries of clinical databases. And that's what I'll focus on today. Now, before I go further, I think it's important to kind of stop a moment and ask the question, why is this important? Why should we care about cohort discovery? To my mind, I think this is rather simple, right? So if we have a researcher and there's no clear path to getting data in order to do that research, that presents a problem. And that's because, data on specific populations, right, a cohort, is necessary to perform research. That research in turn contributes to new knowledge of medicine and health, and that new knowledge in turn can positively impact care and public health, right? And the reality is this is not a problem just for individual researchers, right? Many institutions have hundreds, if not thousands of researchers, right? And so if we're unable to really create that pathway to creating new knowledge and improving health and improving medicine and so on, by just getting data on cohorts in the first place, well, that presents a problem. So to my mind, this is really the motivating and really interesting question in this space. How do we enable researchers to safely and efficiently access and explore patient data for secondary use? It's secondary because, of course, primary use is in the course of patient care. And so my personal philosophy is that researchers should not need to know or care how to use a database in order to do their research, right? Tools to enable access to data should be intuitive, fast, and work with any clinical database, right? They should work with any flavor of data depending on the work we want to do. And last, maintaining patient privacy and safely de-identifying data are really critical, for our patients, for individual researchers, and for institutions as a whole, right? And so I'd like to step back in a time machine of sorts. And we're going to step back, 7 or 8 years or so, and excuse me, and look back at the landscape of cohort discovery tools as I saw them at the time, and I'll kind of give you my thoughts on how I imagine building improvements upon those. So, and I don't mean to pick on any tools in particular, although of course I'm kind of showing logos here. Looking at other cohort discovery tools, a few things I noticed were, first, they tend to only work for a single data model, right? In other words, that means if the structure of a database and the structure of data don't look a certain way, many institutions are simply out of luck. And that means that typically an informatician has to go in and create a fairly complex set of code or procedures to transform data into a way that will work for the tool instead of the other way around. And that can be a lot of work. The next thing is, these tools often assume that data are already de-identified, right? In other words, names, medical record numbers, and so on are stripped out and so on. And the reality is that's often not the case, right? So, this again means an informatician needs to often, by hand, programmatically, essentially, strip out that information, shift dates, and so on. And that can be, both really time consuming and also perhaps imperfect as well. And last, the cherry on top after we jump through all these hoops, so to speak, is we hope that the interfaces for these applications are really intuitive and useful and fun. And I think the reality is that's not always the case, right? And because of that often equates to users requiring more extensive training, and that takes time and so on. And so we're in our time machine and so on. And looking at that time, what I imagined is, what if we took what seems to work very well with these applications, this hierarchical interface of biomedical concepts, but instead within each concept, we essentially embed fragments of SQL or SQL queries, right? Essentially a window or a pointer into a database saying, this is where we find this information, right? And as users drag over those queries piece by piece to create larger queries, right? We can approximate something like an English sentence saying, you will find patients who, in the past 3 years, had systolic blood pressure measured in some way or shape or form. And users, of course, then click run query, and the system stitches together fragments of those SQL queries in order to generate a larger query that can be executed on the database, right? And we execute that and report back to the user how many patients were found. I think the real beauty of this approach is that it's dynamic and open-ended enough to work for virtually any kind of database, not just one or two. And so, again, we're in our time machine, and beyond that, I wondered, what if instead of expecting data to be identified, what if the application could itself dynamically de-identify data based on simply analyzing the metadata of database columns, right? So we strip out names and identifiers, and we shift dates of birth and so on and so forth. And what if we went further, right? As researchers, we often want to know more than just a count of patients. We need to see aggregate visual information. We might need to see row level data in order to perform some analysis. And what if we could do that in a single click of the mouse or something close to that, to make that as easy as we possibly can? And last, zooming out a bit, I wondered, what if multiple institutions could query one another's data in federated networks without needing to share their data directly? And critically, even if they use different data models, right? Even if they have somewhat different flavors of data structure and so on. So these are the things I imagined, and these ideas really coalesced into what became this application called Leaf, which, as I mentioned, I developed around 2015. We've used Leaf in production at the University of Washington since 2018 or so, and these numbers are a little out of date, but that has led to something along the lines of 45,000, maybe 50,000 plus or so queries run in a self-service fashion at the University of Washington. And at any given time, we have somewhere around 300 to 350 active users of Leaf. We open sourced the software for any other institutions who want to use it in 2019. And this is very difficult to measure because it's open source software. Of course, not everyone needs to let us know they're using it. But to the best of my knowledge, there are roughly 15 or so sites around the world using Leaf in production, and another 20 to 30 or so who have piloted or are actively evaluating it right now. Within the United States, that looks something like this map. And you can see it's a combination of academic medical centers like here at the University of Washington, and also commercial organizations and so on too. So I think we've had a reasonable amount of success with Leaf, but as informaticians and researchers, I think it's important that we always kind of keep pushing ourselves and questioning, can we do this better, right? And so one question I've kind of had over time is this idea of, as I watch researchers use Leaf, how intuitive really is this hierarchical interface of concepts? And there's a great kind of publication that touches on this that I've got below if you're interested. But I'm showing here a commonly used lab concept, hemoglobin A1C lab results, and displaying this using the Loink ontology or Loink tree here. And notice how many click, 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 clicks I have to get down just to find that. And is this really the most intuitive way we can present this to users and make this fast and easy? The other observation I've had over time, kind of looking at gaps and trends within the literature, is first, I see a trend towards systems which automatically identify patients from free text, right? From eligibility criteria free text. And there's some great work by colleagues at Columbia called Criteria to Query that does this. On the other hand, though, looking around the literature again, in our time machine a few years back, I didn't see any systems able to reason upon this phenomenon called non-specific criteria, right? And it sounds a little silly, but we see this often, right, in clinical trials, eligibility criteria, and so on. For example, excluding patients with conditions which affect respiration, something like that. And that could be any number of conditions, but we don't want to necessarily enumerate every single one of those, like asthma, COPD, and so on. So I didn't see any systems able to really be able to reason upon this commonly seen phenomena, right? People saying non-specific criteria. Additionally, I think if we are creating tools that purport to be able to find patients eligible for things like clinical trials, it's only reasonable that we would also evaluate our tools for how well they're able to find patients, eligible and able to be recruited, right? But at the same time, I saw very few studies that actually used real clinical trial data for evaluation. And last, I think when we talk to PIs and so on who might use cohort discovery tools, very reasonably often a response back is, this looks nice, but I have an analyst or an informatician within my group who's very good with working with clinical databases, and I don't really need a cohort discovery tool because I trust a human to do it better. So I think that's a very reasonable gold standard, right? And none of the tools that I saw actually compared their performance to that of an experienced human database programmer. And so that was one kind of question that stuck in my mind. So with those questions and those challenges in mind, I'd like to pivot next to this area of natural language processing, or NLP, and look at it from the lens of how can NLP possibly help us address some of these challenges. So I'm going to give this very short shrift in the interest of time. I'm going to vastly oversimplify things a bit, but for brevity, I'm going to say that natural language is language that's created by humans for the use of other humans. NLP, in turn, I'll define as programmatically interpreting, analyzing, or utilizing natural language for some purpose. And there's some examples here on the right. Could be things like information retrieval, right? We want to pull some structured information from text. Maybe machine translation, translating from English to Spanish, so on. Language generation, that's kind of akin to what we see in tools like ChatGPT, so on and so forth. And I'm not going to focus on this today in today's talk, but it's worth mentioning too that the state of the art in most NLP approaches right now is driven by deep learning based approaches, specifically what we'd call the transformer architecture. And again, I won't kind of delve into this, but much of the architecture of the tools I'll talk about in the remainder of this talk do typically use the transformer architecture. So we're in our time machine where we're a few years back looking forward. And what I imagined is, what if we could create an interface where users can simply type free text criteria for patients they're interested in. But as they do so, critically, we have maybe models running in the background and constantly analyzing the input that the user is typing. And that allows us to rapidly give the user feedback, right? Informative feedback saying, this is what I think you mean, and perhaps letting the user know they're on track and their query will work. And then when they click Run Query, what if the system could, in real time, essentially line by line by line, provide essentially a table one, right? Mirroring the inputs that the user typed in to find the patients, but also outputting in a format that's familiar to researchers and hopefully quite intuitive. So that's what I imagined. And the question is, using NLP, how could we get there? And I think there's many possible approaches, right? So this could involve using deep learning models, as I touched on, rules, right? We handcraft a set of rules to create database queries programmatically, right? Or both. If we were to use a deep learning model, typically the common denominator, the real necessity to do so is what we'd call a gold standard corpus or corpora. And this is typically a human expert annotated set of documents or something like that we can use to train models to in the future take in documents they haven't seen before and output in some automated fashion useful information for us to do that task. And so what I imagined is, what if we had an annotated corpus of clinical trial eligibility criteria to help us do this, right? And that could look something like this, right? So if we have a document eligibility criteria related to a breast cancer clinical trial, we could annotate that to look something like this, right? We could annotate that, excuse me, between 39 and 49 years. Well, that's an equality comparison. No is a negation. Breast cancer is a condition, so on and so forth. Right, and so that's what we did. So I and my collaborators extracted just over 1,000 randomly selected eligibility criteria documents from clinicaltrials.gov, and we annotated kind of two key phenomena, again, to kind of help us create this vision, this tool that I showed earlier, right? The first thing we annotated is what we call named entities. And in this context, a named entity is essentially a span of text relevant to a given eligibility criteria. So in this example, we can see increase is a polarity of value high, and polyneuropathy disability is a condition, right? That's hopefully pretty intuitive. The next phenomena we annotated is what we call relations, and relations are semantically meaningful connections between those entities. So this polarity is in relation to polyneuropathy disability, and P&D is an abbreviation of polyneuropathy disability. So hopefully this kind of makes sense. So with this corpus, we were able to train machine learning models to take in criteria like this free text and output these named entities and the relations. And so the question is, are we done? Is that all we need to do in order to generate database queries to find a cohort and really build this? And in my experience, it really wasn't, right? So we can take in a free text eligibility criteria, we perform inference, and the output of these kind of models is, we can imagine this and kind of think of this as a graph of sorts, right? Where the named entities that I mentioned are nodes, and the relations are essentially the edges between those nodes. And the easiest approach is we simply enumerate each of these nodes and step by step using rules, create a query of some sort to find a cohort. What I found though is in practice, this is quite difficult, right? And this tends to be very error prone. One often needs many rules to enumerate each of these nodes and create the right database query, including rules checking other rules. And at scale, this becomes very difficult to maintain and test. And it really, in my experience, did not generalize well to new data. And so in a sense, we were back to the drawing board, and I needed to look at kind of alternative approaches. And one that I came down upon is this, what we'd often call, or what we would call semantic parsing. So a semantic parse is a machine-readable logical representation of the underlying semantics of the input we give it that we can use for some, represent in some way for some particular task. So that's kind of a mouthful, but if we look at this example, right? So women and men over 65 with diabetes and no contraindications to metformin, well, we can represent this in a semantic parse using something like this. And again, the real beauty of this approach is that it's machine readable, and many of the kind of challenges that we find with enumerating graphs and kind of disambiguating relationships between the nodes becomes much less of a challenge with a semantic parse, right? So I'm showing here the very clearly delineated nesting and relationships between each of these criteria that's very difficult to produce, like using that first graph approach I showed. And it's worth mentioning before I move on to, essentially this approach is taking in text and outputting restructured text. And that aligns with what we often use, what we call a large language model, or just a language model for, right? Not unlike ChatGPT. So I'll come back to this point in a moment. So in order to use this semantic parse-based approach and generate queries, I and my collaborators created another corpus. So we called this the Leaf Logical Forms corpus, and we took 2,000 randomly selected sentences or lines of eligibility criteria from that first corpus I mentioned, and that's available here for anyone who'd like to use the corpus or take a look. And using this corpus, we then trained language models to be able to take in free text criteria and output this nice restructured machine-readable semantic parse form. So using these models that I've just touched on, I'd like to pivot next to, again, look at this intersection of how can we leverage these NLP based models in the context of cohort discovery and really kind of create that vision that I outlined earlier. And when we're doing so, again, the goals that I wanted to really achieve that I thought would be novel in this case would be, how could we do so while also reasoning upon non-specific criteria? I touched on that earlier, and we'll look at an example shortly. And then how can we leverage these models to, when we're finding that cohort, generate queries for any sort of data model, right? So the system would work not just in one institution or one database, but work with virtually any institution or database. So I'm going to outline just a few other pieces of this larger puzzle that enabled us to kind of get at some of these challenges. So the first is a knowledge base, or a KB. So I created a knowledge base using what we'd call RDF, or the Resource Description Framework. This is essentially a graph database of triples queryable by a language called Sparkle. Now, core to this is the Unified Medical Language System, or UMLS. But I also included the LOINC to HPO data set, so we could reason that a patient may have a condition given certain lab results, the disease ontology, symptom ontology, potential drug-to-drug interactions data set, and also the COVID-19 ontology. So I'd like to kind of put the pieces together now. When using this knowledge base and using this semantic parse enables us to do what we call multi-hop reasoning and really reason upon these non-specific criteria. So I'd like to give a somewhat silly example, but I think it'll give you a sense of the real power and flexibility in this kind of approach to reason upon kind of biomedical concepts like this. So imagine we have a criteria and someone's looking for patients with contraindications to drugs for conditions which affect respiration. So here we have multiple, essentially nested levels of non-specificity. So we can represent this with our semantic parse in this kind of form shown on the left, and working inside to outside, step by step, using our semantic parse and our knowledge base, our system is able to successfully reason that, among other things, asthma causes changes to respiration. Methylprednisolone can be used to treat asthma, and mycosis or a fungal infection is a contraindication to methylprednisolone. So essentially this enables us to reason upon both the relatively simple non-specific criteria, but also fairly complex ones as well. I'd like to next touch on this, final piece. How do we actually create queries for any kind of database? And I created a system called semantic metadata mapping here, or SMM, that I'll explain next. So a semantic metadata mapping is a machine-readable tagging system for mapping database objects and records to their meaning and usage. And I think this is actually fairly intuitive. So let's look at an example. Let's imagine we have a simple table of demographic information that looks something like this. Well, we can annotate this using UMLS concepts, saying, of course, person ID is a patient identifier. Birth date is a date of birth using this UMLS concept. And notice the semantics or the real meaning of this gender column depend on the value of a given row or tuple, right? So we can conditionally annotate that if the value is F, that means female. If the value is M, that means male. If the value is GQ, that means genderqueer, so on and so forth. And I'm not showing it here, but we can also annotate that a concept or a column has ICD-10 codes or SNOMED codes or something like that as well. And so taking all of these pieces together, the system that I created looks something like this. And I'll briefly kind of walk through an example, although it might be a little tricky to follow. But essentially, the system takes in these free text criteria. We then perform inference using the models that I talked about earlier, right? We determine what the named entities are within these sentences, extract the relations, then transform that into that semantic parse representation. At that point, we still have a string, and so that is then interpreted in memory using what's called a recursive descent parser. We then normalize string values, like the word diabetes, for example, and normalize those into ICD-10 or SNOMED or other codes. Next, our reasoning module and knowledge base using a simple set of rules reasons upon the non-specific criteria I talked about earlier. And last, all of that information is then passed to the semantic metadata mapping and SQL compiler layer, which generates database queries and executes those on a given database. So we still have this question, though: how do we evaluate a system like this? And I touched on earlier, could we use this idea that could we use actual past clinical trial enrollments to really evaluate how well this system runs, or would have run had we executed queries when those trials were recruiting patients? And also, could we compare this system empirically to an experienced human programmer, right? Again, a reasonable gold standard system for finding eligible patients. And so that's what we did. We extracted metadata on 168 clinical trials done in the past at UW between 2017 and 2021. We limited that to only trials where at least 10 or more patients enrolled. And the number of raw lines of eligibility criteria, right? Each trial has a document of bullet points, essentially, of criteria that patients must meet. We intentionally chose those on the shorter side, 30 or less lines, in order to kind of have a reasonable starting point to test this system. For each of those 168 clinical trials, we grouped them by the condition field in clinicaltrials.gov. And working with our clinical collaborator, we determined 7 conditions of interest to test. We randomly chose 1 trial per condition, except in the case of cancer, where we chose 2 for 8 trials total. And here's the key part. So we gave we essentially passed that eligibility criteria information for each of the 8 trials to our system called LeafAI, and also to a human programmer, each essentially with instructions to generate database queries to find eligible patients. We executed those queries on what's called an OMOP database, a large extract of the University of Washington's EHR data in the past 20 years. And we limited the data available in each of those queries to essentially try to simulate the data that would have been available in the past when these trials were still recruiting patients. The human was instructed to skip criterion which could not be computed, like consent and things like that, and also reason about non-specific criteria where possible. And last, both LeafAI and the human skipped criteria where 0 patients were found. And this was really a pragmatic step because we know that, nonetheless, patients did enroll in these trials, and there are always, things that we cannot necessarily control for, like gaps in our data. So skipping cases where we found 0 patients was a kind of pragmatic way to kind of avoid some of those pitfalls. And here's what we found. And this is, maybe the most important table I'll show today, but it's also one that kind of takes a moment to make sense of. So each of the 8 trials is shown on a row here. The number of criteria is the number of raw lines of eligibility criteria, those bullet points. So one way to read this table is from shortest trial to the longest, or in some sense, the easiest to the hardest to find patients for. Enrolled is the number of patients who actually enrolled in the trial according to our electronic health record. So we see 83 patients enrolled in the lymphoma trial. Matched under LeafAI is, after the system had executed queries to find eligible patients, the number of patients found eligible who actually matched those enrolled. So LeafAI here found 80 of the 83, or 96%, with 3,200 or so eligible, compared to the human programmers, 77 of the 83, or 92%, with 2,300 eligible. And that took the human programmer about 1 hour to execute, or to write the query, rather. So we can see in both cases, for both LeafAI, the system, as well as the human programmer, there were a number of cases where 0 eligible patients were found, or those matched did not actually enroll in the trial. So this is a difficult task, but it also gives us a sense of, how challenging it really can be for an experienced human programmer as well. If we look at the mean match rate, again, this is essentially mean recall, right? LeafAI had a mean percent of 43.5 compared to 27.2% for the human programmer. And that took the human programmer roughly 26 hours to write these queries versus a few minutes on my laptop for LeafAI. So I think this table gives us a sense at a high level of how the system compared to the human, but it really doesn't give us a sense of step by step where the LeafAI system and where the human programmer differed and maybe executed different kinds of queries. So I'd like to look at a few examples of trials at a deeper level to kind of get a sense of that next. So this is the multiple sclerosis trial. Here, this visualization shows here on the y-axis, we have percent recall. Again, that's that kind of match rate. The x-axis is the line number in this eligibility criteria document. So essentially, we're going line by line by line by line, looking at the different queries executed to find patients at each step. And what we would want, ideally, is for LeafAI in blue and the human in orange to be at 100% match rate from start to finish. Of course, we don't necessarily see that here. So the first kind of real drop in recall for LeafAI we see at line 10. This was an exclusion criteria for current shift work sleep disorder, or narcolepsy. And what we found is LeafAI actually excluded patients with diagnoses for drowsiness, snoring, and so on, because those happen to be child concepts of sleep disorder within the UMLS. And the human programmer did not do that. For both, though, on line 12, we see a drop in recall that's about the same, right? This was an exclusion criteria for current stimulant or wake-promoting agent use. And notice this kind of washout period of sorts within 30 days of screening. Well, neither the human programmer nor LeafAI knew when that screening period occurred for each patient, so each cast a wide net over time looking for stimulant orders. And what we found is many patients actually had orders for stimulants within our data. It's just that we don't know when that 30 days of screening occurred. So looking at one more example, this is for the type 1 diabetes trial. We see that from the start, both LeafAI and the human programmer performed reasonably well. This was, the first criteria was looking for diagnoses of type 1 diabetes by a certain age. The human happened to use A1C labs. LeafAI used diagnosis codes and found a few more. For both, though, we see a significant drop in recall on line 4. This was a criteria to look for insulin orders or insulin infusion. And what we found is very few patients in our data actually had insulin orders. And we hypothesized this was not because they weren't taking insulin, but rather because they likely had their insulin filled at outside pharmacies outside of UW. So we wouldn't have that information. So just to recap, I presented LeafAI here, and this is the first system to directly compare to and in some cases rival or surpass the capabilities of an experienced human programmer in finding eligible patients for clinical trials. And to the best of my knowledge, it is the current state of the art in this task. So I've talked about creating a system that is able to find eligible patients by simply typing this free text. I'd like to pivot next to looking at how we actually make that useful and intuitive for researchers to really make this system as impactful as I hope it would be. And to do so, I created a web application for LeafAI. Again, the idea being it is a NLP-driven self-service application for cohort discovery. And the user interface, I think, is the interesting piece here, right? So I imagined a chat-like interface, and I hopefully most of us are familiar with this paradigm of things like Teams and Slack and so on, where past actions and inputs are shown above, and as we scroll down below chronologically, new actions and responses are shown. And I created this interface with a real eye towards first explainability of system actions, right? So we could understand if the system is saying it found 500 patients, really getting a sense of, excuse me, what logic and so on went into finding those patients. And in the larger picture, the goal here is iterative exploration and editable system responses using what we call multimodal output. And I'll unpack that in just a moment. So here is a screenshot of the user interface. So we can see user inputs in the top right and the system responses in the lower left. So looking at this explainability challenge, I think it's easiest to understand this with an example. So imagine we are using a tool like this to find patients, and we're typing for a minute or maybe several minutes, and we make a typo. We misspell some condition or something like that we're interested in. And we click run query, and the system responds with 0 patients or error or something like that, and it's not clear why, right? So in the immediate term for us as users, that's essentially wasted time. And if this repeats and continues to occur, that'll lead to likely uncertainty and lack of trust in the system, right? So to avoid that, I created a solution where the system performs named entity recognition and normalization as the user types, right? So as I'm typing, we can see that the system highlights and kind of allows us to hover over different concepts, which we can kind of get a sense of, are we on the right track? Does the system know what I'm talking about? And we can understand that as, in certain cases, normalization success, right? So we can see that, oh, great, we've typed a BMI. The system seems to understand that means body mass index in this context, and here's the definition. But also normalization failure, and I would argue that this is useful information as well, right? So if I've misspelled diabetes mellitus as I'm showing here, this, the fact that the system still couldn't understand, so to speak, or couldn't normalize this value is useful to us too, because it potentially saves us a lot of time, right? Because if we can simply correct this spelling mistake, we can avoid that confusion that I talked about earlier. And this extends to explainability in terms of query results as well, right? So imagine that we've asked the system to reason upon what contraindications to metformin could be. Well, after a query is executed, the system will actually show us what it determined could be a contraindication, and perhaps as users or researchers, some of these concepts might not be useful to us. So we can simply hover, hover over those and uncheck those that that we're not interested in, and re-execute the query without having to retype the whole thing. And similarly, as the query is running, the system is able to use what we call a streaming interface, and in real time, kind of step by step by step, let us know what it is doing and what it's found. So this might not seem very important in this example when this query I'm showing here takes 11 seconds, but we can imagine in a real clinical trial or with a long list of criteria, queries that take several minutes, right? And if we get no visual feedback for, say, 3 or 4 minutes, I think it's reasonable for most users to ask, is the system doing anything at all, and perhaps just walk away, right? By using the streaming interface and letting users know step by step where the progress is at, the goal here is to gain user trust through transparency. And ultimately, to kind of bring it back, the larger aim here is to save time, as I said, through transparency, through faster iteration, and build user trust and confidence in the system. All right, so I'd like to end today, kind of taking a step back and looking at the large language models and other systems and so on that went into creating LeafAI, and look at other directions and research areas we could use to build upon and kind of make this even more potentially useful. So I'll be talking about autonomous agents, ambient AGRs, and other directions. So I think in the larger picture, hopefully most folks on this call are familiar with this phenomenon called, hallucinations, where when we ask something like ChatGPT, for example, to respond to or answer or output some information, the response is based on what we would kind of imagine to be hallucinated information that was not grounded in anything we provided in the input, right? So essentially making up a response, but seeming to do so, right, with perfect confidence. So this challenge may never quite completely go away, although I would expect it to be much less of a challenge in the future. On the other hand, large language models are still potentially incredibly useful due to the open-ended nature of their output, right? So I can ask a large language model to, for example, write a database query to find some information for me. I could also ask a model to perhaps explain possible reasons for some social phenomenon, right? And it could respond to me as well. The common factor here being that these are both kind of text or potentially images or other things as well. To my mind, I think the real relevant research question in this space is then, how can we leverage large language models to understand and respond to our inputs in an actionable way, provide useful information and context transparently, citing external sources, and I think most critically, decide upon reasonable steps to achieve a goal, right? I think I'm less interested in simply having a chat or getting some text output than actually leveraging these tools to achieve goals that would save time and really make people's lives easier. So one direction I'm working on right now is what I'm calling RedBot. So for folks who are familiar with the RedCap research data capture tool, RedBot is essentially an LLM-driven, what I'd call a semi-autonomous agent, right? It's a LLM-driven system that's able to, it's designed to kind of automate and handle some of these tasks that would typically take even a fairly smart and well-versed human, maybe an hour or more to accomplish, right? So for example, let's imagine we have a user and they're saying, I'd like to collect structured variables for various symptoms related to Kawasaki disease in a form. suggest how to structure the form, then implement it in my projects and cite your sources along the way. And what Redbot would do is then report that, first to determine the symptoms of this, I'm going to search trusted sites on the internet. I found several possible sources. I'm going to now kind of try to make sense of them and parse them. And maybe the Mayo Clinic website lists symptoms such as fever greater than 102, rashes, enlarged lymph nodes, and so on. Here's a citation. I'm now going to call the REDCap API and determine how to incorporate that into your project. And I'm done. I would suggest adding the form Kawasaki syndrome symptoms with these kind of REDCap specific field and notations. Shall I update your project with this change, right? So automating these fairly, cognitively, maybe not extremely challenging tasks, but time consuming and somewhat challenging in certain cases. That's the real goal here with Redbot. And we can take this further, right? So imagine we're using an LLM agent-driven system to attempt an end-to-end clinical research study, right? So imagine we have a user that says, I'm interested in recruiting patients with long COVID and tracking self-reported symptoms and conditions after an index diagnosis in weekly intervals. And so here are some eligibility criteria and so on. So as humans, we can imagine this to be a larger task that we can break down into simpler subtasks, right? And the question is, can we use LLM-driven agents to accomplish this? I would argue we possibly can. I would argue we can, for example. So, we could use something like Redbot to create a custom REDCap project. LeafAI could then identify eligible patients and pre-populate data from the electronic health record, after patient consent. On that note, a consent agent could generate consent requests, maybe by an EHR patient portal or text message, something like that. And last, a contact agent could call patients weekly over the phone, analyzing transcripts and send symptom data to REDCap in a structured way, right? And between all of those would be an orchestration agent managing agent-to-agent communication, right? Managing these subtasks within the larger task. I do have a working proof of concept. I've been working with Sean Mooney on this contact agent, this LLM-driven phone call concept. But I think there are many, many challenges and caveats to this as well before I move on, right? So would an IRB ever approve this, for example? I think it's a question we wouldn't know until we try, right? There are a number of other directions I think we could also take this in, right? So imagine within LeafAI expanding capabilities using perhaps something like the GPT-4 model from OpenAI or others to expand our scope to open-ended general purpose question answering, right? So don't just find me a cohort, but let me ask rather, and then you answer questions about that cohort, or even dynamic visualization generation and so on. We can imagine cases where large language models auto-suggest tweaks or changes to our criteria because maybe for a given recruitment in a clinical trial, maybe we're unintentionally excluding historically underrepresented patients and rural patients and things like that, and providing a citation and suggestion for how to rewrite that. We could take that even further, right? So imagine a human and LLM jointly driven phenotyping algorithms as well. So I think there's an enormous amount of possibility here. So what I'm really talking about is, right, so large language model driven reasoning and automation combined with friendly and intuitive and explainable user interfaces. But what I'm really, really talking about is creating systems that make a positive impact on health and enable us to be better informed, less distracted, and more connected with one another, right? And I'd like to end on a positive, maybe a bit controversial note. So my question is this that? Is the way that we are currently integrating large language models into the electronic health record, is that enabling us to be better connected, less distracted, better informed than we were before? Or instead, are we simply grafting large language models onto what's in fact, perhaps an antiquated and really inadequate system to do really the work we need to do in research and improving patient health, right? And are we not perhaps missing an opportunity to really reimagine what an EHR should be? So what if an EHR was an unobstructive ambient system, for example, that could seamlessly respond to gesture and voice, that could generate explainable visual interfaces dynamically as we need them, that could answer patient questions with empathy, or that could prospectively and actively predict health outcomes as a core function of the EHR. So I hope that someday I can contribute to building something like this. And for anyone interested, please reach out. I'd love to talk more. So thank you very much.